All right, so I'm going to give you guys, as promised, a week 7 lecture quiz review. So it went over chapters, if you would have seen, right? Chapters 19, 20, and 21. So chapter 19 went over the kidneys, right? So the renal system. So remember the functions of the kidneys, right? They're going to be able to filter, reabsorb, and secrete. Those are going to be those main functions of the kidney for the most part. Of course, you're going to have other functions of the kidney, whereas, the regulation of your extracellular fluid and your electrolyte balance, all right? We also have pH regulation, as well as hormone production, right? So it produces those hormones, right? So hormone production, okay? Where we're going to create or produce vitamin D3, right? Calcitriol. We're going to produce renin, excuse me, and we're going to produce erythropoietin, right? So remember all these functions. And so when we look at filtration, remember that filtration is going to be from the blood to the lumen, all right? So that's from the blood to the lumen. And that filtration is only going to occur at that renal corpuscle, so between the glomerulus and that Bowman's capsule, okay? And then when that plasma is then filtered over, it's now called it's now called filtrate, right? And typically, you're not going to find like large proteins, red blood cells, white blood cells, or anything like that in that filtrate. It's, because those things, they're too large. They should not have passed through those barriers. And I'll talk about those barriers in a second, okay? But typically, you should find, glucose, sodium, potassium, calcium, things like that, right? Would have been easily filtered over. Now, even though you just easily filtered those things back over, another function of the kidney is reabsorption, right? And so those materials, right, in that filtrate, they're going to pass back into the blood, okay? So, for example, they'll go from the lumen back into the blood, okay? So, lumen, oops, right? You're going from the lumen back into the blood. And that's going to occur along those peritubular capillaries, right? So, again, only filtration happens within that glomerulus capillary. But the reabsorption and the secretion, that's going to happen along those peritubular capillaries, okay? And again, reabsorption is you're passing those materials back from the lumen back into the blood. And secretion, it's a selective process, but this is where we're moving materials from the blood into the lumen of the tubule. So it's basically in the same direction as filtration. Again, but it's going to occur along those peritubular capillaries, okay? So remember what that renal corpuscle is. That renal corpuscle is simply that glomerulus plus the Bowman's capsule space. Okay, all together, this makes up that renal corpuscle. Okay. Now, for that filtration to happen, filtration is the mass movement of materials from one area to another area. Right? And again, we know that filtration is going to occur in that renal corpuscle. And so the substances that are going to be filtered, they must pass through a couple of barriers, right? To then enter the lumen, right? Which is right here, right? The lumen of that Bowman's capsule. So it's going to have to go through that fenestrated capillary, right? That glomerular capillary endothelium. So this is the endothelium of the actual blood vessel wall, the endothelium of the glomerulus capillary, right? And these fenestrated capillaries, or this capillary endothelial wall, is going to have negatively charged pores, right? And remember, these negatively charged pores in this wall is going to repel that of those negative proteins. It's going to repel that of those red blood cells. So thus, you're not going to find negative proteins and red blood cells, that is going to pass through because it's inhibiting them from passing through, right? So you have the fenestrated capillary as a barrier. You have the basement membrane as a barrier. That's going to, again, exclude most of those plasma proteins. And then you have the Bowman capsule, right? Those podocytes, right? And those massogenous cells. So those podocyte foot processes is going to be on there. That's going to be creating those filtration slits that we see. But again, you have the fenestrated capillaries, you have the basement membrane, and you have these podocytes, all acting as a barrier of substances that's going to pass from the blood into the lumen. So remember that equation that we talked about before. Excuse me. And I love this image because it shows filtration from the blood to the lumen. It shows secretion from the blood to the lumen. It shows reabsorption from the lumen back into the blood, right? But remember how to calculate the amount of solutes that is ultimately excreted from the body? That's going to be the amount that is filtered minus the amount that was reabsorbed plus the amount that was secreted. That will ultimately give you the amount that was excreted. So what did you actually pee out, right? What you filtered through minus what you reabsorbed back into the blood plus what you selectively secreted into the blood, okay, will equal the amount that's excreted. So there's a couple of pressures that will cause, filtration. So you have the blood pressure, right? The capillary blood pressure, which is that hydrostatic pressure. And that hydrostatic pressure is the pressure that's in your blood vessel, right? In that glomerulus. And this hydrostatic pressure is this pushing force. And so it's the force that pushes fluid out of that area. And it's pushing fluid out of the blood vessel, obviously into that Bowman's capsule. So that's promoting filtration, right? So that favors filtration. But then we have the capillary colloid osmotic pressure. And that osmotic pressure is a pulling force. So you're pulling fluid into this area. So you're pulling fluid into the blood vessel due to those plasma proteins, right? And so if you're pulling fluid into the blood vessel, obviously that opposes filtration, right? Because it's pulling that fluid back into the plasma, okay? And then we have the capsule fluid pressure. And so this is the pressure that's in the Bowman's capsule. And so this, again, is that hydrostatic pressure that's in the Bowman's capsule. And again, the hydrostatic pressure is that pushing force. So this is that pushing force that's pushing stuff out of the Bowman's capsule. And if it's pushing it out of the Bowman's capsule, it's pushing it back into that capillary. So that, again, opposes filtration, okay? So the glomerular filtration rate must be constant, right? It's going to be relatively constant. But that glomerular filtration rate, that GFR, is going to be simply the volume of fluid that's filtered per unit of time, right? And so this is where we have that glomerular filtration rate is the amount of fluid that filters into that Bowman's capsule per unit time. Okay, so, and that's going to be influenced by the net filtration pressure as well as that filtration coefficient. Okay, and again, your body has this the ability to auto-regulate itself and maintain a constant glomerular filtration rate over a wide ranges of different blood pressures. Okay. Also, bring to your attention, remember, that glomerular filtration rate, it's an average around like 125 mils per minute that we're going to be able to filter, or 180 liters per day. It's really important to understand that this glomerular filtration rate will indicate the health of your kidneys, though. Okay, how effective are your kidneys at doing their job at filtration? That's going to indicate their health, right? And we can indicate that by the glomerular filtration rate. Now, like I mentioned, your kidneys can auto-regulate themselves, right, over wide ranges of different blood pressures to maintain that 125, or that I should say 180 liters per day of filtration. So, and it really is because of that myogenic response, right? The smooth muscles, especially like of your arterioles, they can contract by themselves, right? So they have that intrinsic ability to respond to those different changes in blood pressure, right? Hormones, right? Your autonomic nervous system, they can also influence your glomerular filtration rate by changing the resistance in your arterioles and altering that filtration coefficient. You also have tubular glomerular feedback, right? And this is where you're sending a paracrine or a local signal from one cell that will influence another cell, like right next door, right? And so we have that juxtaglomerular apparatus. And in that apparatus, we have the macula densa cells. Remember that the macula densa cells will detect salt, meaning these macula densa cells are chemoreceptors, right? Because they measure the amount of a chemical, that salt chemical, right? Sodium chloride. Then you have these granular cells. These granular cells will secrete renin. These are those renin-releasing cells, those granular renin-releasing cells, right? But ultimately, these granular cells, gotta remember, right? These are baroreceptors, right? So they sense pressure, okay, in that kidney tubule, okay? And this is all going to be in that that juxtaglomerular apparatus at that afferent arterial region, right? So talked about filtration, mass movement of molecules, right? Filtration only occurs in that renal corpuscle from the glomerulus to the Bowman's capsule. Another function of the kidney, right, is reabsorption. And again, reabsorption is going to occur along those peritubular capillaries, right? And so we got to remember those peritubular capillaries, they're going to reabsorb fluid all along the entire length of that nephron, right? Or that kidney tubule, okay? And so when we're looking at reabsorption, again, it's from the lumen of the tubule back into the blood, right? And again, it's going to happen within those peritubular capillaries, right? So sodium is going to be reabsorbed in that proximal convoluted tubule, right? Glucose is going to be reabsorbed in that proximal convoluted tubule, but glucose needs sodium to be reabsorbed. So it's going to be that those sodium-linked glucose transporters, right? That's going to be able to accept glucose from the lumen, right, and pushing it back into that interstitial fluid, back into the blood ultimately, right? And then we also have some secondary active transport that these are going to be symported with sodium, right? So movement, again, like glucose, like I mentioned, amino acids, and some other organic molecules too. We do have some transporters that will also use hydrogen instead of sodium too, so that's important to know. Secretion is another function of the kidneys, right? And so this is basically the active movement of molecules from extracellular fluid back into the, right? The lumen of the nephron. So again, secretion, a selective process. We're secreting it from the blood into the lumen, right? So we're secreting it out of the body ultimately, right? And this is going to be important for homeostatic regulation of potassium and hydrogen ions, for example, right? And if we increase the amount that is secreted, we can increase the amount that is excreted, right? So things that are filtered through, of course, a lot of that stuff is going to be reabsorbed. But if we can add into that, we can add some stuff, right, via secretion, we can add to the amount that's going to be excreted, right? So we looked at that secretion of penicillin, and so the body will freely secrete penicillin as well, right? So that secretion enhances excretion, like I mentioned, by simply removing solutes from the peritubular capillaries, right, back into the lumen, okay? And so potassium, hydrogen, right, variety of organic compounds, these are going to be secreted, right? When we looked at chapter 20, we looked at integrated physiology 2, right, fluid and electrolyte balance. And so when we talked about water reabsorption, right, we talked about the mechanism of vasopressin, or ADH, right, antidiuretic hormone. So ADH, that is antidiuretic hormone, it's produced in the hypothalamus, but it's stored and then subsequently released in the posterior pituitary gland. And so it's going to be released, of course, when there is a drop in blood pressure, right, or a drop in blood volume, right, or there is high, osmolarity. Okay, too much solutes in the body, essentially. And so what it does is it tries to retain fluid. Okay, so vasopressin will basically stimulate those aquaporin channels to be inserted in the apical membrane. Okay, and so you can see that, of course, vasopressin, this polypeptide hormone in the blood, it binds, right, to cell of the collecting duct, and it ultimately, again, like I mentioned, it stimulates the aquaporins to be inserted into this membrane right here. Okay, thus we can reabsorb water back into the body, right? Conserve our fluid volume. Don't pee it out. Okay, again, vasopressin stimulates the insertion of those aquaporins in those collecting ducts. And like I mentioned, right, vasopressin, when it's released, it's released when you have low blood volume or low blood pressure, but even stronger stimulus for the release of vasopressin is going to be that plasma osmolarity, right? If plasma osmolarity increases, that's going to be a stimulus to release vasopressin or ADH, okay? And that stimulus is even stronger than a drop in blood volume or blood pressure. Aldosterone, on the other hand, right? So aldosterone is a steroid hormone, right? That is produced by the adrenal cortex, specifically that zona glomerulosa. It's a mineralocorticoid. And so aldosterone gets signaled, right? And we'll talk about that in the RAAS cycle in a second. Aldosterone gets signaled to be released from the adrenal cortex. Aldosterone then goes to the kidneys. And what it does is it goes to the distal tubule and it turns on those sodium potassium pumps, right? It turns on the sodium potassium pumps. So ultimately, we're going to reabsorb sodium, right? And we can then reabsorb water, thus maintaining our blood volume, maintaining that blood pressure to increase it ultimately. But because it's turning on that sodium potassium pump, right? You're going to be able to reabsorb sodium, but you're going to secrete potassium. So aldosterone has an important role in sodium potassium balance. Okay. Again, aldosterone is going to be released, goes to the kidneys, turns on those sodium potassium pumps in that distal tubule for sodium reabsorption and potassium secretion. But remember, when you reabsorb sodium, you're going to reabsorb water, thus increasing your blood volume and increasing your blood pressure. And this RAAS cycle, right, stands for the renin-angiotensin-aldosterone system. This is going to be a pathway that ultimately maintains blood pressure, right? This pathway, excuse me, this pathway will get stimulated, right, when we have a decrease in blood pressure. When we have a decrease in blood pressure, right, we will then release renin. Okay. So there's a few ways that we talked about in the session, right, of a few stimuli to release renin. Ultimately, when renin is released, its ultimate job through this cycle is to raise blood pressure, right? So, for example, if you have a drop in blood pressure, right, our cardiovascular control center will recognize that, our medulla, right, our cardiovascular control systems, and then we will turn on our sympathetic activity. Our sympathetic fibers will then innervate those granular cells in the afferent arteriole. Those will then tell those granular cells to release renin. So that's one way, right? Your autonomic nervous system can turn on renin to be released. Another way to produce renin, right, is if you have a drop in blood pressure, you're going to have a drop in that glomerular filtration rate. And so less sodium is then going through these macula densa cells. These macula densa cells, right, will then produce these paracrines, right? These localized signals that will go from one cell, and it goes to these granular cells, tell these granular cells to, again, release renin, right? So that's two stimuli to release renin, right? Or if you have a drop in, blood pressure, right, that's a drop in pressure, right? And so these granular cells are those baroreceptors. And if they sense a drop in pressure, then they're going to release renin, right? So there's a three-pronged attack, essentially, for renin release. And so when renin is released, ultimately, it converts the already circulating angiotensinogen in the plasma into angiotensin I. Angiotensin I is a mild vasoconstrictor, but clinically we ultimately want angiotensin II. Angiotensin I is now in the plasma as it was, converted from angiotensinogen. Angiotensin I is in the blood. It's going to travel in the blood system, right? It then passes those blood vessel endothelium in the pulmonary system, the pulmonary circuit, that's going to contain this ACE hormone, angiotensin converting enzyme. And then that's going to convert angiotensin I into angiotensin II, right? Angiotensin II, obviously now, is going to be a powerful vasoconstrictor, okay? So it's going to vasoconstrict, thus increasing blood pressure, okay? It's going to go up to your medulla, tell your medulla to increase cardiovascular response, right? That's going to increase your blood pressure. Excuse me, right? Increasing the contractility of your heart, increasing the heart rate, right? Putting out more blood into the arterial systemic supply. Angiotensin II is going to go to your hypothalamus, right? Tell your hypothalamus to release right, vasopressin. So now we have increased ADH or increased vasopressin. Now we can conserve more fluid volume. If you can conserve more fluid volume, you're going to raise your blood pressure. It's going to tell the hypothalamus to increase thirst, right? So now you'll seek out fluid, right? Increase volume, increase blood pressure. Angiotensin II will also go to the adrenal cortex, right? Tell the adrenal cortex to release aldosterone. Aldosterone will then go to the kidneys to reabsorb more sodium, right? You reabsorb more sodium, you reabsorb more water, right? Increase your blood volume, increase your blood pressure, right? And it'll directly tell those proximal tubules as well to reabsorb more sodium. So angiotensin II does a lot of things ultimately in its job to raise blood pressure. And all that was stimulated with the release of renin. So we have acids and bases that's going to come from many different sources, right? So acids are going to come from like dietary inputs, right? Like amino acids, fatty acids from your diet. You even produce acid from like metabolism, right? CO2 production, right? Keto acid production, right? That's all going to modulate that blood plasma pH levels, right? We don't typically have a lot of bases that's coming into your diet, though, for the most part. But essentially, what enters should be what exits, though, when we're looking at that. Okay. When we're looking at vitamin D, is really important too, right? And our extracellular fluid, right? Especially to maintain the proper levels of calcium. So, if we remember, parathyroid hormone, PTH, is produced by the parathyroid glands. That's going to be posterior to your thyroid gland. So, parathyroid hormone, it aids in calcium reabsorption in that distal tubule, right? If there is low calcium in the body, right? So, a stimulus for parathyroid hormone is basically low calcium in the blood. This is a stimulus to release parathyroid hormone. Parathyroid hormone then goes to the kidneys, right? Indirectly tell the kidneys. So it goes to the kidneys and it tells the kidneys to produce vitamin D3, calcitriol, right? That's then going to go to the intestines to increase intestinal absorption of calcium, right? It'll also go to your bones, right? Tell your bones to upregulate those osteoclasts to put more calcium into the blood too. Vitamin D is a really important vitamin, right? It's a steroid hormone, but it's important for calcium and phosphorus reabsorption, or I should just say calcium and phosphorus absorption. Okay. And so when we're looking at the synthesis of vitamin D, this is going to be important to note, right? The synthesis of vitamin D, right? Because we remember we're going to have a few different organs that's involved in creating the biological, active form of vitamin D3. That's going to be the skin, the liver, and the kidneys, right? And so remember, it's the cholesterol that's in your epithelial cells, or the cholesterol that's in your cell membrane, right, in your skin, that then gets converted, right, to a form, and then that gets sent to the liver, then that ultimately gets converted and then gets sent to the kidneys, right? And so we can see this process right here. It goes from 7-dihydrocholesterol to cholecalciferol to 25-dihydroxyvitamin D3 and then 125-dihydroxyvitamin D3. Okay, so remember that as well. I also just wanted to mention too, just briefly, that blood buffering system. Right? As is always going to be important too. So for example, remember from ventilation and the things we have carbon dioxide. When carbon dioxide is in the plasma, it mixes with water, right? And so in the presence of this enzyme, carbonic anhydrase, right, it converts this reaction to forming carbonic acid, right? Carbonic acid is a weak acid, though, of course, so it like dissociates into hydrogen and bicarbonate. Okay, but remember, this is facilitated to get to carbonic acid via the presence of carbonic anhydrase enzyme. Okay. Chapter 21 looked at the digestive system, and so remember the different phases of digestion, right? The cephalic phase, everything above the stomach is going to be the cephalic phase, right? You're thinking of food, your mouth is watering, you're starting to salivate, things like that. That's all the cephalic phase, right? Everything that's happening with digestion that's above the stomach. And then we have the gastric phase, and that's going to be the stomach, what's happening in the stomach. And then we have the intestinal phase, and that's after the stomach. That's what's happening in the intestines, right? Absorption, for example, right? So remember, these are the phases of digestion: cephalic, gastric, intestinal. The gastric phase, right, is going to have these gastric secretions, right? And we're going to have activity of these secretory cells of the gastric mucosa. So you have these G cells. These G cells are like these Go cells, all right? They produce gastrin, right? Gastrin then stimulates gastric acid secretion. So gastrin, right, then goes to the chief cells, goes to the parietal cells, tells the chief cells to produce pepsinogen, right? Tells the parietal cells to produce what they need to produce, which is gastric acid, hydrochloric acid, right? And an intrinsic factor, right? So ultimately, the G cells produce gastrin, and gastrin stimulates the production of hydrochloric acid, okay, from the parietal cells, like we mentioned. So remember, chief cells produce pepsinogen. Parietal cells produce hydrochloric acid and intrinsic factor. Hydrochloric acid, right, will activate pepsin. So this pepsinogen down here, when it's in the presence of hydrochloric acid, it converts into pepsin. Pepsin now digests proteins. Okay? Intrinsic factor is important for our absorption of vitamin B12. Okay. So remember fats, right? Triglycerides are going to be digested into monoglycerides and like free fatty acids, so like by those lipases and the colipases. It's the bile, right? The bile that is produced in the liver gets stored and subsequently released from the gallbladder. It helps to emulsify that fat, so when those lipases, those colipases come in, they can break the fat apart much more easier, right? And so again, like I mentioned, fat digestion is going to be facilitated by those bile salts, okay, which emulsifies that fat. And so essentially, right, most lipids, obviously, they're not going to be typically water soluble, right? So they're going to form like these large fat droplets, as you can see, right? And a lot of times fat be coming in the form of triglycerides, especially in certain diets, right? But bile is stored and concentrated in the gallbladder, and then it's sent to emulsify that fat. Notice how those bile salts, they literally go around the fat and literally just pulls it apart. And then those lipases, those colipases can break it down even further. And then we can reabsorb the fat or those fatty acids into these lacteals, into the lymphatic system. And that's how we get it into the actual systemic supply. I also want you to look here as well, all right? So that bilirubin is, when we're looking at bilirubin metabolism, it occurs in the spleen, in the liver, and the intestines, as well as the kidneys. And so we have this enzyme metabolism, right? The heme oxygenase then gets converted to the biliverdin reductase, and then we have the glucuronal bilirubin transferase, okay? So remember this enzyme metabolism stage. When we're looking at the intestinal phase, right? So once that chyme enters that small intestine, the intestinal phase will begin, right? And so digestion and absorption of nutrients is going to be completed in the small intestine. Most of those absorbed nutrients is going to go right to the liver, right? Via that hepatic portal system, right? Before, of course, it enters the systemic circulation. So whatever, you reabsorb, it's going to go to the liver to get cleansed, right? Before it goes into the blood, okay? Happy studies.